All right, so welcome back. We're looking at lecture 2-2, 3-1, kind of a little bit of both. Right, in the actual semester here, what has happened is that Thursday's class was canceled, and normally I like to do one set of lectures for a week, so we get 2 full lectures out of a single set of slides. But with the snowstorm and some other scheduling things going on, Thursday just didn't work out. So this is a little bit of a weird in-between. Last time we got most of the way through chapter 2, or rather the week 2 slides. This time around, I'm thinking we'll finish that out. We'll start looking at the beginning of week 3, and then in the next lecture, we'll finish out the week 3 slides, and then we'll be back on a little bit more of a regular schedule. So, how's about, let's pick up just a little bit before where we left off last time. Last time, we were focused a whole lot on defining energy. Talking about energy, talking about the different ways that we could have energy, for example, how we can actually change the energy of an object, right? And we change the energy of an object. We said any sort of change like that is coming from work. And work has a very specific definition in physics. Work is a force acting over some distance. So that is to say, you can push on anything, but if it's not moving, you're not actually doing work. But if you're pushing something and it is moving, you might be doing work. There's one last condition we actually need. You have to be pushing on that object, or pulling, I guess, but a force, one way or the other. You have to be pushing on that object. The object has to be moving, and the third condition is that you have to be pushing in the direction that that object is moving. And I always like to use the example here of, let's imagine you've got a car that's been broken down, you've got a couple friends helping pull, and so everybody's doing a little bit here, and let's imagine you've got that one friend, and we've all got that one friend, that is just pushing on the side, standing on the passenger side, pushing on the passenger door, while everyone else is behind the car trying to push it forward, trying to get to that next gas station. Is that friend helping? I think in that situation, it's pretty clear. No, they're definitely not. Right? In a best case scenario, I guess, they're trying to steer the car one direction or the other, but just use the steering wheel. So the people behind the car, pushing the car, right, their force is going in the direction of motion. They are doing work on that car. They are putting energy into the motion of that car. The friend pushing on the side, not so much. So those are the conditions we look for. And actually, mathematically, while we're talking about this, there is a way to describe how much a force is going in the direction of the motion. And that's with this cosine of theta here. So what this cosine of theta is doing is it's basically saying, let's imagine your force is not exactly pushing in the direction of motion, but kind of is, right? It's not exactly on, it's a little bit up and diagonal, so not all of the force is actually going into the direction of motion, but some of it is. That some of it is actually calculated out if you take the force, if you multiply it by cosine of that theta. Then you get exactly how much of that force is going in the direction of motion, and the rest of it wasted. Not a big deal, but wasted. So, let's get back a little bit into this. We talked about how we can have a potential energy. And a potential energy is very special because it's kind of like work waiting to be done. So when I'm thinking about one of the most common ways that we consider this, gravitational potential energy. If I lift an object up, my pen for example, right, and lifting this object up, gravity is now waiting to act on this pen. Right? Because what happens, as soon as I let it go, it falls. And I need that so I can't lose it. But as soon as I let go of this thing, gravity is more than happy to take over. It pulls the pen down, so the motion of the pen is downwards. The gravitational force is downwards, so it is doing work. And all of that work, I can imagine, when I lift this up in the first place, I can imagine that it's work waiting to be done. As soon as I let go, that work is going to be performed. The pen's going to pick up some sort of kinetic energy, and we have motion. And there's actually a way to calculate that out. And we do so with this equation right here. So that is to say, when we're talking about this gravitational potential energy, how much energy that object has is the mass of the object times how high that object actually is, times this gravitational constant g equal to 9.8. Those three things together, when you scale them up like that, that is how much energy that object has in weighting. And there's also this very key part here. We talked about this problem last time, but the main takeaway was that energy in all systems must be conserved. Energy can't be created, it can't be destroyed, it can only be transformed. So in a case like this, when we lift up this object and we drop it, it started with all of this potential energy. As it starts to fall, as h gets smaller, we start to see that the potential energy decreases. Where does it go? It goes into the kinetic energy. By the time we're right above the ground, right, a millimeter above the ground, almost all of the potential energy has now been converted into kinetic energy. Transformed, not created, not destroyed. So, there are some forces that act and are not so kind about storing energy, and friction is probably the number one that we would want to think of. So there's a way to calculate the friction force, but we talked about this a little bit last time, so I'm just going to go over this briefly. Friction takes energy away. It's always doing negative work, no matter what. And the reason why we consider it negative work, because any object that's moving, we call that mechanical energy. Right? Something that's moving can transfer that moving energy into another thing, can be transformed between potential energy, can do all of these transformations very readily, very efficiently. But when friction gets involved, friction dumps that energy into places like heat and sound and scraping away at the material itself. And those three are not mechanical energy anymore, right? Anytime if I push a piece of furniture, any heat, any sound generated by moving that across the floor, that doesn't go into moving the furniture. It's never going to come back into moving the furniture. So we consider it lost energy, but really what it means is that energy has gone somewhere that we just can't easily get back. So, we talked about some of the different forms of energy, but I think let's go back to this. This is where we ended last time, talking about some of the common units that you might see. And we've got a lot of different units. Some of them are kind of legacy units at this point, stuff that we used from the imperial system that don't get used too much anymore. Some of them have some other practical uses, like barrel of oil equivalent is very nice when you want to be trying to measure up, you know, if we're trying to kind of compare economies of gasoline in cars, different things that we can do. Gasoline is a very prevalent thing in our mind, right? Because it's used so frequently. So when we're trying to compare like a barrel of oil's worth of energy, suddenly that's, you know, not exactly something that we can conceptualize, but a little bit closer. It gives us some sort of frame of reference. Now, there's a slightly different table here. This is not different units, but this is like an energy density or an energy content of some different fuel sources. So these are a handful of different, we called this last time, not last time, a couple times ago, primary sources, original places where energy comes from. Coal, oil, gasoline is a secondary source. Natural gas, primary or secondary, depends on if they extracted it directly from the well or you can refine it later. Biomass, hydrogen gas is another one we typically produce on our own. So I guess not entirely primary sources, but a lot of primary sources and a relative value for how much energy we can get per kilogram out of that material. And this one is a little bit strange. I use the word energy density, but it's not exactly energy density. Energy density was how much energy can we pack in a certain space, in a certain volume. This is measuring energy versus kilograms, which definitely is not the same, right? Kilograms is mass, but oftentimes they go with each other. Something that has a very high energy density is probably also going to have a really high number here, energy per kilogram. So this gives us a rough way to compare some of these different fuel sources. And especially if you're a shipping company, again, thinking about traveling with all of this energy that you need to carry from one location to another. Generally, very frequently at least, a lot of trucks do very much care about the weight, the mass that goes into those trucks. So if you can get more energy for the same amount of mass, that's usually pretty appealing. But we can see some of the classical sources we've got here, right? Coal versus oil versus natural gas. I think these numbers alone give us a pretty good idea of why that trend where we see natural gas going up in usage, coal going down, and then oil is still frequently in use because, I mean, realistically, cars are still running mostly on gasoline. So that's kind of, we've got this tier system, but it's really a lot of why coal is just not coming back very much as any sort of fuel source, right? It will continue in some locations to see use, but, widespread growth especially, probably not growth. Biomass. Some countries actually use this as a fuel source, and what this is basically, you can have a lot of different sources of biomass, realistically. It is something that has died. Typically plants are the most common thing that we use for this. Algae, moss, peat moss is used a lot for this. Some sort of burnable, flammable organic material. If you waited a few million years, this material would eventually turn into oil. But, as we've talked about before, a few million years a person does not have in their lifetime. So if we're thinking about energy sources that we can use today and have regenerated maybe in a decade or so, biomass is not a bad candidate for that. Uranium, comparatively speaking here, one thing that I do want to watch is when we're looking at this number, the units here are quite special because all of these megajoules, 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 suddenly we're looking at gigajoules. And if you're not aware of what these numbers are, a megajoule is 10 to the 6th regular joules. We look at something like gigajoules, and now that's a 10 to the 9th. So comparing these numbers, what we're actually looking at here is that for natural uranium, exactly as we mine it with the isotope distribution and all that good stuff, if we wanted to compare it more accurately with these numbers above, what it really is 580,000 megajoules per kilogram. There is a lot of energy to be extracted from nuclear. But nuclear fuel, there is not a ton of uranium in the world, right? Especially when you compare it to something like coal or oil. There's not a ton of uranium in the world, and realistically, we still don't have a very good solution for getting rid of the waste. So that's one of those things that we've got kind of on the back burner right now. Maybe one day we'll be able to scale this up a little bit more if we can figure out some better solutions for some of these technical problems we run into. The science is mostly solved for this. Really what it is at this point, it's just kind of an engineering and practicality setup that we really need to conquer at this point. Now, hydrogen, deuterium, nuclear fusion. I don't want to take this number too seriously. This is 330 terajoules. So that is 330 million megajoules. But here's the problem. We've got this saying that if somebody tells you something is 1 year away, it's actually 5. If it's 5 years away, it's actually 10. If it's 10 years away, it's actually 20. And if it's 20 years away, maybe someday. And nuclear fusion has been 20 years away from a successful reactor for about 50 or 60 years now. I'm not saying that it'll never happen, right? And we've actually been successful in creating some very small-scale fusions. But effectively, what you're trying to do in this problem is you're trying to create a miniature star on Earth, control that miniature star, and then extract energy out of it. And it's possible, but the engineering behind that is incredibly difficult. And we have been able to do some fusion at this point, but usually those cases we see, we're putting more energy into the system than we're getting back out. So it's not practical as an energy source yet, but I am holding out hope, maybe someday. I honestly kind of expect that it might be in my lifetime, right? It might be in our lifetime. I'm not that much older than you guys. I'm holding out hope for it, but it's not there yet. So don't take this number to heart. So when we compare this to power, right, this value that we've talked about, the rate of energy usage, when we talk about a watt, 1 joule divided by 1 second is 1 watt. So a 100 watt incandescent bulb, like the total standard light bulb that you would see, that is 100 joules every single second that it's turned on. So here's a problem, working with some numbers here. We had this statistic that in 2019, the whole world used about 540 quads worth of energy altogether. What I want to know is, can we take that value and convert it into watts? Maybe to try to give us a little bit of a sense of scale versus like our 100 watt incandescent bulbs, our 10 watt phone charger, laptop chargers more like 90. So pause this video, work through this problem a little bit, see what kind of number you can get, and if you'd like to, you're always welcome to drag and drop that answer box so you can see if you've actually got it. But now I'm assuming that you've had the chance to look at this a little bit on your own, so let's talk about it together. Let me show you how I approach this. When I need to do unit conversions, I typically like to set up a lot of fractions. So this isn't actually too difficult. Let me talk about what I mean. So let's look at the energy first. We have 540 quads. I know that there are 10 to the 15th BTU for every 1 quad. I also know that there are 1,054 joules for every 1 BTU. So at the end of the day, we can calculate out this number. So when we run through all of these numbers, what we find as a total is 5.69 times 10 to the 20th joules. Certainly not an insignificant number. So that's great, but that's not watts, right? And you might have approached this problem and done this conversion, got all that stuff right, but there's a missing piece here, right? Because power is supposed to be energy divided by time. What is the time? Well, it's this full year, the per year portion. So we also need to do a conversion for that, right? Because we can't plug years into watts. So let's take time. We're going to start with 1 year, and we'll do this step by step. I'm going to say, okay, in every single year, there are 365 days. 0.25 if you want to include the leap year, but so every 365 days, there are 24 hours in every single one of these days. There are 60 minutes in every single one of these hours, and there are 60 seconds in every single one of these minutes. And I guess there's one last thing that I forgot to do on this last one that let me go ahead and show it right now. The reason why I set it up like this is because now when we're looking at the fractions like this, I have Q divided by Q. I've got BTU divided by BTU. That's why at the end of the day, we end up with joules. It's the only one that didn't get canceled out. So looking at it here with time, the same thing applies. Years cancel out. I've got days on top and bottom. I've got hours on top and bottom. I've got minutes on top and bottom. The only thing that lives is seconds. So when we put all of these numbers together, I get a grand total of 31,536,000 seconds. The last step, power is equal to energy divided by time. Divide these two values, exactly stacked how we've got them right here, for a final answer of 1.8 times 10 to the 13th watts. Not a very small number. So not really super helpful, right? At least when I'm thinking about a number like this, I'm trying to wrap my mind around how many light bulbs is that worth. That's another really hard thing to conceptualize, right? The number on its own just doesn't mean a whole lot to me. But sometimes, some of these units have this practical effect of you can consider converting to other units, like barrels of oil equivalent, where suddenly it's a little bit easier to wrap your head around how much that would actually be. So keep that in mind. There are more reasons to use these units even if they're not standard, right? Even if I don't like to work with them, they're still useful sometimes because they can help us better understand the problem that we're looking at. So I've got another problem here that I do want to look at real fast while we've got the chance. In this case, I want to expend 100 kilocalories, or 100 calories written as on the cereal box. But let's say I'm on some sort of new workout routine, right? So I'm trying to burn 100 full capital C calories in my exercise session. I'm working on some sort of machine, because I'm not a big fan of free weights personally, but I'm working on this machine and it tells me that I am expending energy at a rate of 270 watts, right? So a little bit above what we talked about before of just doing regular squats. This is a hard workout, right? This is really starting to get you moving. This is hard cardio. The question is, how many minutes do I need to exercise? Pause the video, think about this a little bit, come back when you feel like you've got maybe a good approach on the problem, a good leg on it. So again, I'm assuming you're coming back here. Let's talk this through. The main issue that we're running into is that 270 watts is a very comfortable, clean unit. Technically, 270 watts, being a power, is joules per second. Joules are not the unit of energy that I want to be looking at. Calories are, or kilocalories, I guess. On the other hand of this, I don't want to be working with seconds either. I'm asking for how many minutes, right? I don't want to count to 1,000 or something while I'm trying to do exercise. The minutes are a little bit easier to read. So what we need to do is we need to convert both of these units. And here's how we can do that. Let me go ahead and start by taking this power. 270 joules per second. So the first thing that I want to do is I want to convert one of these units, and I'm going to do it exactly like we did on this last problem. 270 joules per second, let's convert joules to kilocalories. So let's go back up to our table. Let's take a look at what this references, right? We see one small calorie, one regular calorie is 4.184. So a kilocalorie, or the capital C calorie, again, the one that's on our cereal box, that is 4,184. Whoops, I've done this backwards. See, now I've run into a little bit of an issue because 4,184, I don't even necessarily want to be, well, no, this is a good way to do this, but 4,184 shouldn't be on top because I'm trying to cancel out the joules. The 4,184 was the joules. So here's what we actually need to do. 4,184 joules on bottom, kilocalorie on top. Okay, so that's going to take care of that conversion. Those are canceled out. Now we just need to convert the seconds. Now, seconds are on the bottom here, so we need to be careful with that. That means we need our seconds to be on top. So when we do this conversion, we land with minutes on bottom, like we're expecting here. We'll see. This will make a little bit more sense in just a minute. So I will say that there are 60 seconds in every 1 minute. That is an equal conversion. Now we can go through again. We say, okay, the seconds cancel out. We are left with this conversion right here. Now, this is not our final answer. It's not our final answer, but it is a step of the way there. It's almost there. We're converting this power into units that we're actually interested in. And when we go through this conversion, what we land on is 3.87 kilocalories per minute. So if you've ever heard of that saying of it is much easier to avoid the calories than to burn them off later, this is a lot of why. It takes a significant amount of effort and exercise to actually burn any sort of real appreciable number of calories. So keeping that in mind if we're thinking about healthy living and healthy eating. But anyways, we've got this 3.87. Now our last step here is we know the total energy that we want to expend is 100 kilocalories. So what I can do is I can take that total energy, I can divide it by our rate of using that energy, and I'm left with the time that it's going to take to do it. And now if we do this, we've got 100 kilocalories divided by 200 and, oh, not 270, that was from before, 3.87 kilocalories per minute. The kilocalories cancel out. I've got like this nested fraction thing going on, and what that means is that the minutes come back up for a final answer of 26 minutes, about 26 minutes. So, in retrospect, we've got a few equations here, right? More than a few, we've got a lot. But we've tried to organize them all right here, right? And remember, the way that we name variables is oftentimes trying to go at least a little bit with what the variable actually is, right? V is velocity, F is a force, M is a mass, A is an acceleration, W is work. So we've got all of these things that at the very least kind of help us remember what they're supposed to mean. But what I'd recommend is if you're a little bit confused about these equations, write them down and just have a tiny little blurb next to them about what they're trying to do. It's a useful place to be with a lot of these equations. The last thing that I want to talk about in week 2 stuff is this particular problem that's showing up in your homework. It's a tough one. It's a little bit of a longer problem, I'll admit. But there's a pretty extraordinary claim, and to make an extraordinary claim, you need extraordinary evidence. What is the claim? The claim is that buying an SUV over a standard car is wasting as much energy as leaving your refrigerator door open for 7, made that mistake in the lecture, didn't correct it before now, for 7 years. So, that's something, right? That's certainly a number. Because realistically, even if we think about it like this, a typical refrigerator running on 400 watts is typically not running all the time. For the most part, it only needs to run very occasionally, especially like right after you've opened it. Some of that cold air escapes and it needs to pull that warmth back out. But a refrigerator that's left open is always going to be running, right? It's never going to stop running. It's going to be constantly trying to pull that warmth out of there, and it never can because it's always exposed to the open room. So that's a condition that's actually going to make things a little bit easier for us, because what that tells us is that whatever sort of time frame we're looking at here, the 400 watts is always going to be happening. Now, where a lot of this difference comes from is in the fuel efficiency, or I guess the average fuel efficiency of each of these vehicles. So notice here, we've got a lot of different units that are not necessarily standard. And one of the ways that you can approach this is not necessarily converting these miles per gallon or anything else like that, but what I'd recommend is using the number that we've got here for the energy per gallon and taking that unit, so keep in mind what that unit actually looks like. This is 40 kilowatt hour per gallon. If you multiply that by miles per gallon, or I guess divide technically, you can cancel out the gallons and you don't need to do any sort of energy per gallon conversions. You can just take this value as we've got it right here. So the problem is not exactly addressing the 7 years, but it does show us in a single year how many years of refrigerator running is that worth. So I wanted to talk just a little bit of brief overview of this problem. I know it's a little bit of a longer one. It's pretty wordy. So this is a fantastic time if you're struggling with this problem a little bit or you're not sure exactly how to approach it. I really do recommend go ahead and work on this with some of your classmates. Right? They're here to help. You've each got some gaps in knowledge, and what you can do is help patch those gaps in each other's knowledge. So that's going to close out what we've got here for chapter 2, week 2, I should really be saying. Let's take a look at week 3. Let's get through the beginning of this, right? Because this is where we really start to talk some of the more practical aspects of energy. Thinking about something like thermal energy. Thermal energy is the inherent energy of a hot object. We talked about this last time, right? It's the buzzing around of the individual atoms of that object. Sometimes we call this internal energy instead of thermal energy because the idea here is that technically thermal energy is kinetic energy, but it's not kinetic energy like a car driving down the road, right? In the case of a car driving down the road, all of the atoms collectively are moving down the road. In the case of thermal energy, all of them are right there just kind of buzzing around in place. It's a little bit different. So, thinking about heat, heat is not the same thing as temperature, but there is a relationship between the two. Heat is any time we are transferring thermal energy between two objects. Objects do not have heat. Heat is a name that we give to energy in transit, right? So there's no like internal heat necessarily. Heat is energy in motion, going from one place to another. So I've got a couple questions to ponder here, right? And if you'd like to take a minute, I'm going to run through these a little bit more quickly, but if you'd like to take a minute, I'd suggest pausing, looking through these slides yourself, and thinking about each of these. Carrying a can of gasoline from the garage to the lawnmower. Gasoline burns, but it's not thermal energy. Carrying the gasoline, I'm doing work, exerting a force over distance, but it's not actually thermal energy, not heat. Boiling water on the stove. Probably heat, right? The burner gets really hot, transfers some of that to the water, it boils. Microwaving a cup of water to boil it. This is strange. At the end of the day, the water's still hot, right? I'm going to come back to this one. Losing energy from your house through the windows and doors, that's another heat, right? There is warm air on the inside. Over time, it slowly kind of warms up the windows, and those windows eventually transfer that warmth to the colder outside, right? This is why double pane windows are such a nice thing, because they help slow that transfer down. Movement of air from the Earth's surface into the upper atmosphere. So thinking like cold fronts, warm fronts. That is another form of heat. It's not quite standard like some of these other ones that we're talking about here, but it is another form of heat. Getting warmer because you're near a fire, surely, or increasing in temperature, or hoping to at least, right? That's got to be heat. Pumping air into your bicycle tire, which raises the temperature. You might not know that this is a common thing that happens, but actually, when you increase the pressure of a gas, it does start to warm up. But it's not actually heat. We're not taking an open flame to this tire. We're not adding warmth to it. What we're doing is we're packing more and more atoms in there. The increase in the temperature is not necessarily because we are putting heat into the system. It's just putting more pressure there. Getting higher pressure heats things up. Raises the temperature. I need to be careful about my language here. Raises the temperature. Heat is not necessarily being added though. Last one, shaking water to raise its temperature. Another one, technically this isn't heat. This does technically happen, right? Agitating something does over time raise its temperature. But it's not heat, it's not that thermal conduction. So looking at these things. This one right here, this is the one that I said we're coming back to. It's pretty unique. We need to get just a little bit more information before we can really address this one. So let's come back to that in just a little bit. For now, let's talk about temperature. Temperature isn't exactly thermal energy, but what it is a measure of how much are those atoms buzzing around. So something that is buzzing around more has a higher temperature, something that's buzzing around less has a lower temperature. Now, there's another rule here, that heat only flows from high temperature to low temperature, never the other way around. This is given by the second law of thermodynamics. And let me tell you, there are some laws that we can kind of skirt around. some situations that it doesn't apply to. But the laws of thermodynamics, we have tried very hard to break. Very hard. Trust me, if we can break the laws of thermodynamics, that opens so many possibilities, especially when we're looking at the energy economy that the world is at right now. But every single time, the laws of thermodynamics prevail. They're unbreakable. So, it's a little bit of an issue. Heat only flows from high temperature to low. That's it. Now, temperature, you could also call it the average thermal energy of the particles inside of any object or substance. Materials that have a higher density of materials are going to take more energy to actually increase that temperature then, right? Because there's just more of them. If it's how much they're buzzing around, then every single individual particle is going to need that same amount of energy to start buzzing around all over the place. I've got to put a lot more energy in because there's just more things there. The lowest energy that we could ever get, or the lowest temperature that we could ever get, is a value that we call absolute zero. And it's technically a bottom out of that temperature, but it's not one that we're ever actually going to be able to achieve. And we've gotten very close, but it's not something that's actually possible. There are some other physics getting in the way of getting to a value like absolute zero. But we can get really cold besides that. Actually, in fact, I work in a lab where the atoms that we work with, we lower them down to a temperature of 40 microkelvin, which for context, outer space is 3 Kelvin, and Earth is somewhere around 300. So, some fun comparisons there on the numbers. We've got some different temperature scales to look at these, and real quick, let me make a correction that I'm seeing here. I've got one typo. Let's just get rid of that. I don't like that scale. I've got a personal vendetta against that scale. See, what it is, you might notice here, when you're looking at these different scales, Kelvin starts at 0. And right now, it's the only one to do so. It is the temperature scale that we like to use in physics and chemistry, because when we're actually dealing with equations that require temperature, we need our very bottom value to be 0. If our very bottom value is something like negative 273 or negative 460, then all of our equations just fall apart. They don't actually work anymore. Our bottom value needs to be 0. And to get to Kelvin, from Celsius, it's pretty easy. All you have to do is add 273. That is to say, like, the degrees of the scale exactly match. Going up 100 degrees Celsius is exactly the same as going up 100 Kelvin. The only difference between the two is the starting point. Now, Fahrenheit was not developed like Celsius was. It is not as directly compatible, but there is a conversion, and that conversion is 5/9 times this temperature in Fahrenheit minus 32. So for one, that tells us they've got a different starting point, but also how they move up is different in each scale. Now, this other scale, this one that I'm not talking about, let's go ahead and take a look at it, see what we've actually got here, the Rankine scale. I don't like this one, largely because if you notice, it is indeed an absolute zero scale. So if we're thinking about using this within chemistry, within physics, we could do that. The reason I don't like it is because Kelvin is such a standard. Nobody in science uses Fahrenheit. Why would you make an absolute scale that scales with Fahrenheit, but it just doesn't make any sense? I think the Fahrenheit scale is fine. I usually prefer it for things like outdoor temperature. When I'm doing science, I prefer to be in Kelvin. I understand some people like Celsius. I'm fine with those 3 scales. But the Rankine scale, in just a personal opinion on the matter, is so incredibly useless. It shouldn't be here. It doesn't belong to be here. Just get rid of it. I don't want to talk about it anymore. Let's go ahead and look at a problem. So, the lowest natural temperature ever recorded on Earth is negative 120 degrees Fahrenheit in Antarctica. What I want to know is if we wanted to convert this to the other 2 useful scales, what would those numbers look like? Take a minute, pause the video, try to work through this one, see if you can get this number yourself. And I know that you can just look this up on Google immediately, but you're missing the point. right? Make sure that you're doing this by hand. Get a little bit of experience with what this equation is actually doing. And now, I'm assuming you're coming back from such an experience. So we're in luck in this case, because both of the equations that we see here, the things that we're interested in are kind of already solved out for us, right? There's no algebra to do here. So let's start with Celsius. All we really need to do is plug in this quantity to what we see here. Negative 127 minus 32, this whole thing, times 5/9. So when we plug in these numbers all together, what we end up finding in Celsius is negative 88.3 degrees Celsius. Still really chilly, but negative 127 was pretty chilly too. So last thing we need to do with Kelvin, this is the easiest conversion. All we need to do is take this quantity right here, add 273 to it. When we add 273 to it, what we get, temperature Kelvin, is 185 Kelvin. Which doesn't sound that bad, right? But comparatively speaking here, right, Kelvin has a very different scale of values. So again, think about this, that Earth has an average temperature of around 303, 313 Kelvin, somewhere in that span. Outer space is 3. So Antarctica's pretty cold, but it's got a long way to go before it's starting to get like what the rest of the universe is. So let's go ahead and keep looking here. There are a couple different varieties of heat transfer. Conduction is probably the easiest way to think about this, right? You touch something hot, you feel that it's hot. That is heat transfer by contact. Two objects touching each other, one of them a different temperature than the other, heat is transferred between the two. Convection is a little bit different. But this is exactly what you see in a pot of boiling water, right? The boiling water, you see the bubbles come up, hot water rises from the bottom where it's warmest. It rises up to the top because when it heats up, it expands ever so slightly. It expands ever so slightly, becomes a little bit less dense, and so it floats up to the top. The cold water, exposed to the room air outside, is going to be cool. It's going to condense just a tiny little bit, and because it's just a little bit more dense, it falls to the bottom, where it heats up and the cycle continues. This also happens in a much more complicated way for the Earth's atmosphere. You've heard of like the multiple jet streams that we've got, the polar vortex currently hitting us right now. Those are all different examples of different temperatures of air moving around with each other and transferring some of that energy simply by moving into another area. So like a bunch of warm particles, a bunch of warm air moves into a certain location, does its own little conduction thing, gives away some of that warmth, moves back into some other location, picks up some heat again, and goes back and forth. Right, so it's kind of like a heat transfer by proxy or a conduction by proxy. You have to move the actual thing that's a little bit more warm. Radiation is the last one. And this one's a little bit strange, and I'm going to have plenty of words to talk about on this one later. But radiation it's got a couple different terms. What it generally means is the particles are flying away from something. And in the case of temperature and heat, those particles flying away are photons, light. So when we look at this first example, whoops, a little too far here. This one that we put a pin in, I gotta be honest, I lied a little bit here. And if you were in the class with me, I talked a little bit about this. I talked about some of the reasoning why I lied at first. But what it actually is, this effect down here, this one that we look at and we say, of course, you're by a fire, you're warming up. There's heat coming from the fire hitting you. That's actually not any different from what a microwave is doing. Part of the difference here, and why I want to split hairs a little bit, is technically, objects with temperature are emitting this broad spectrum of all the different colors of light. And there's a lot of different colors of light, right? We've got our visible spectrum, but that's only a very, very tiny portion of the full spectrum. The full spectrum of light goes all the way from radio waves at the very low energy side up to microwaves, still pretty low energy, visible, now we've got like a medium amount of energy, then we get into ultraviolet or UV, gamma rays, X-rays on the really far end of super energetic light. Our eyes can only pick up this very narrow band of it though. And the reason we think, at least, why, is because this very narrow band, it happens to pass right through water. Water doesn't interact with those colors of light. So if the world is covered in all of this water and we want to be able to see through that water, it's pretty helpful to be able to see that little tiny spectrum of light that water doesn't pick up on. Not all colors of light are as equally passable with water. But part of the difference here is that when we're microwaving a cup of water, what it really is, it's kind of like a radio antenna. This radio antenna is constantly generating out these radio waves. They're high energy radio waves, so they're actually microwaves. But these microwaves are not necessarily coming like you would normally get them from some object that's actually hot, right? There's nothing that's actually getting really, really hot inside of a microwave. It's just radiating this light as if there was something hot. So it's a kind of no, it's a kind of yes, because technically it is radiation. But it's not radiation from a hot object. It's a little bit of a different kind of radiation. So I kind of group it in. It's a yes and a no. The fire, though, actually transfers most of its heat in exactly the same way. You might not realize this, but fire does burn with some amount of visible light, right? But the majority of the light emitted by a fire, the overwhelming majority, in fact, is not actually visible light. It's infrared, a frequency of light that our eyes aren't too sensitive to. But that infrared energy is still coming to us. We still feel it on our skin, on our clothes. It does still warm us up. Most of the air, the hot air just rises up and doesn't actually transfer that much energy to us. So it actually depends on the light to transfer that energy to you. Another example of this is walk outside. Well, during the day. Right now it's nighttime, so that's not super helpful. But if you walk outside during the day, you feel the warmth of the sun on your face. That's light. That's energy being radiated away from the sun, right? There's no conduction there. There's not anything in between the earth and the sun. So there's no way that there's some sort of material transferring that heat. It's light hitting you. And the sun's light is about 40% in that infrared range, about 40% in the visible, and then about 20% in the really high energy ultraviolet. And that's a lot of the reason why you need to wear sunscreen outside, because that high energy is quite dangerous. But it really only starts to come about in a meaningful way when something is really hot like the sun. So, now that we've talked through that a little bit more, I am going to have some more words to talk about radiation later on. We're going to have to spend a little bit of time understanding what light actually is and all these different colors. But I think for now, let's call it there. We've got plenty of stuff to talk about next time around. We'll kind of go into each of these in a little bit more detail, discussing some of the things that we can calculate with these, discussing a little bit more about each method and the equations we can use to describe that. So, thanks for being here, and I'll see you again next time.